This is a lecture for the planar systems in which there will be two non-equal real eigenvalues and neither of them will be zero. So this will give us the saddle, source, and sink phase portraits, and we're going to take the solutions all the way through. We're going to find the eigenvalues, then we'll find eigenvectors, and we'll draw the phase portraits. We'll do the three canonical for saddle, source, and sink, and then we'll do one non-canonical example. So just in general, if we want the solution for the planar system, we have to find values for the eigenvalues. That would be lambda 1 and lambda 2. Then we'll have to specify the eigenvectors. We haven't done that at all. And we'll also look at what are the equilibrium solutions. We start with the eigenvalues. So what we're going to do here will be the canonical example. And if you remember, the canonical example was a very simple matrix, coefficient matrix A, and then we get phase portraits that are lined up with the coordinate axis and have the most simple symmetric looking pattern. So the simplest matrix for two eigenvalues is the diagonal matrix done right here, and in general could have something here. It could be A and B, say. These are zeros. Okay, so you only have entries on the diagonal. A is not equal to B, and they're neither 1 or 0. We don't want to deal with the zero eigenvalue in this case. Okay, it will turn out that these entries on the diagonal are the eigenvalues. They are lambda 1 and lambda 2, so in the simplest case they're just named lambda 1 and lambda 2 because they are the eigenvalues. For a triangular matrix this holds too, but we're going to use the simplest one, which would be the diagonal matrix. So we'll have to show that these truly are the eigenvalues. Whatever you have on the diagonal will be the eigenvalue, and I'll show that in a minute. So recall from the previous two lectures that the eigenvalues are the values of lambda that satisfy this equation. The determinant of A minus lambda times the identity matrix has to equal 0. Okay, so if we set that up, remember that A we called, okay, I'll write A here again just so you can remember it. A is, and we just called this lambda 1, and we didn't show that it really was the eigenvalue yet, but it will be. So we're looking for these values of lambda, and so we subtract them. So A minus lambda I will look like this. You have lambda 1 minus lambda because of the I business, and then a 0, 0, lambda 2 minus lambda, and we want the determinant of this. So what's the determinant of this system? It's just and we know that that's 0. That's already in factored form. We don't have to go to the quadratic equation. If you recall, let's go to the quadratic equation just to show that this is true once I finish this up. Okay, so you have here, you want this to be equal to 0. You want to find values of lambda that satisfy this equation. Obviously, you're going to have two of them. One of them is lambda is going to be equal to lambda 1. The other is going to be equal to lambda 2, thus showing that indeed the entries on the diagonal for the A matrix, for a diagonal A matrix, are the eigenvalues. So instead of solving it like we did the obvious way, just because of how simple this situation is, let's look at that quadratic. Okay, in general, we know there's a characteristic polynomial that lambda has to solve, and it's going to look like this. This is a good review, even though we didn't really need it here. T is the trace of the matrix A, and D is its determinant. And then in general, the solutions would look like T over 2 plus minus the square root of T squared minus 4D over 2. Okay? So if I substitute it in here, okay, what is the trace of A? The trace of A in this case would be, and the determinant So remember A was like this. So here's its trace, lambda 1 plus lambda 2. The determinant is the product of the two minus 0, so we'll just call it like that. All right, if I substitute that into this equation, well, actually, you can work through the steps. Okay, I have to clear the board here. I want to leave the other information up. That's why I'm doing it this way. Okay, so we know that T is this. D is and we're looking at lambda equals T over 2 plus or minus the square root of T squared minus 4D over 2. So you have lambda 1 plus lambda 2 over 2. And what's under that square root sign? Okay, T squared would be, okay, lambda 1 plus lambda 2 squared, and it's going to be minus 4 times lambda 1 lambda 2. Working this out, you've got okay, so you subtract off that 4, you'll end up with lambda 1 squared minus 2 lambda 1 lambda 2 plus lambda 2 squared, which is just, okay, that's what's under the square root sign here. So taking the square root of that, we have plus or minus and the solution would be, okay, if you take the plus sign, you'll have, right, because the half lambda 2 over 2 and minus lambda 2 over 2 will subtract off. If you take the negative sign, okay, so we got the same result both ways. I just wanted to show you that the other way in general does work. So now we have two eigenvalues, and they're not equal to each other, and neither one is 0. So now we have to find the eigenvectors, and we haven't done that before at all. So the eigenvector is a solution of this equation where lambda is each one of the eigenvalues. So you take each eigenvalue and you put it in here, right here, and you find V1. Then you put in lambda 2 and you find V2. There's two eigenvectors corresponding to these two eigenvalues. Alright, so when I put lambda 1 into this equation, and remember what A was just that diagonal matrix with the eigenvalues on here. So when I put lambda 1 into this equation, this turns into a 0, and then I always have another 0, always have another 0 here, and now you have lambda 2 minus lambda 1 times those two components of the eigenvector right here, and that has to equal the 0 matrix, or the 0 vector. So how do we find these? Well, write it out. Sometimes you can just glance at it and see what it says. Okay, what does the first line say? It's going to be 0 times Vx1 plus 0 times Vy1 equals 0. Well, that's not very helpful. Vx1 could have any value, and Vy1 could have any value and still satisfy that first equation. The second one, more informative, 0 times Vx1 plus, now it's the difference of these two distinct eigenvalues. Okay, this is not 0, so this has to be 0. So Vy1 has to be 0. Vx1 can be anything because it's going to be multiplied by 0. So since it's going to be anything, you always pick the simplest anything. 0 is not going to be too helpful, so we'll pick 1. Right? And so here is here's the first eigenvector. Here's the first eigenvector. We let Vx1 be 1. It could be anything it wants, so we always pick 1 when it can be anything. And the y component has to be 0. So you'll notice this lines up with the x-coordinate axis. And as I mentioned before, for these canonical phase portraits, you do have the eigenvectors lining up the coordinate axis, which makes the phase portraits very simple. So now we repeat the process to try to find the second. Whoa, that's supposed to be a 2. Okay, we're looking for the second eigenvector. So we substitute in the second eigenvalue, and here's the second eigenvector, duly corrected. Recalling that A is, so you have these zeros on the over here off the diagonal like you always had, and lambda 2 minus lambda 2 gives you another 0 here, and then you have this term. Okay, what are the eigenvectors? You're looking for the components vx2 and vy2. So I'll just write these out, and it's so similar to the other one, you'll see what's going on. Okay, the last equation just has zeros against both vx2 and vx1, so it doesn't offer any more information than what we're going to get from here. Okay, the two eigenvalues, lambda 1 and lambda 2, are different from each other, so this is not equal to 0, so this has to be 0. On the other hand, 0 is multiplying vy2, so vy2 can be anything it wants. We'll pick a 1. So here is the second eigenvector. Okay. Again, this is along the coordinate axis. This is along the vertical coordinate axis. Now we have a two-dimensional system. It's a planar system. There are two equations, and we expect that if we could have a basis, this is a linear system, if we could have a basis, we would need two linearly independent solutions. After that, all solutions can be written as linear combinations of the two. So here is our first solution, y1, which is e to the lambda 1t times the first eigenvector, and similarly, here's y2, it's e to the lambda 2t times the second eigenvector. Are these linearly independent? Well, all you need is to show that v1 and v2 are linearly independent. If you have two vectors and you want to show they're linearly independent, put them together in a matrix. So we'd have 1, 0, 0, 1, and check the determinant. This determinant is not 0. They are linearly independent. If they're linearly dependent, then they are multiples of each other, and the determinant would be 0. Okay, so these are the eigenvectors are always going to be linearly independent. Right? So now we can take any solution or all the solutions, and they can be written as linear combinations of y1 and y2, and here is the solution right here. Now you have the solution. Like I say, we don't spend a lot of time graphing the solution or studying the solution. Instead, we look at the phase portraits. The solutions can vary considerably depending on the choice of C1 and C2, which of course come from the initial conditions. This is a particularly simple case, and that's why we did it. If I write these solutions out, what is x? X of t is going to be C1 e to the lambda 1t, but that's a 0 for the next term, so it's, doesn't have that other term. And y, well, the first one's zeroed out. This is pretty much a decoupled system here, but again, we're looking at the canonical systems, which are simple. Let's look at the equilibrium solution. If you remember, there were two choices for equilibrium solutions for these kind of systems. One was what's called a trivial solution, and that was the origin. And the second was an infinite number of equilibrium solutions, and they would occupy a line through the origin, so they would include the trivial system itself. And what the determining factor between these two cases was the determinant of A. In this case, the determinant of A is not 0. In this case, the determinant of A is 0. So if we look at A again, well, we already figured out what it was anyhow. So here's A. We'll just write it again. Lambda 1, 0, 0, lambda 2. And we want to take the determinant of that. So the determinant of A is going to be neither 1 or 0 by our, because that was our initial assumptions for this case. So this determinant is not 0. Therefore, the only equilibrium solution is the trivial solution at the origin. Now we can start looking at the phase portraits. For this case, we can have one of three types of phase portraits: saddle, sink, and source. If the eigenvalues have different signs, then we'll have a saddle. If they're both negative, then we have a sink. If they're both positive, we have a source. So the source, both eigenvalues are greater than 0. And now I think it's sort of informative to see what's really going on in the phase portrait, because I don't know, I think it can be confusing. So what I've drawn here are the eigenvectors. So here's the eigenvector v1, here's the eigenvector v2. Okay, and they are lined up with the coordinate axis because this is a canonical system, and that won't be the case for the non-canonical example. Now, here was the solution. So first we're going to say that C1 is 1. This is just to demonstrate something. And C2 is 0. So this is off the boards, and we're only looking at the solution, e to the lambda 1t times v1. Well, multiplying that vector. What does this mean? That means if we start here, say we start here, we're going to start on the vector v1 because there was no other place, and the e to the lambda t determines how fast, you could say, we move along this vector. Right? If you start on an eigenvector, you stay on it. Okay. Now, because these are positive, we're going to be moving in this direction. If lambda 1 is very big, we're going to be moving in terms of t very fast. If it's small, we will be moving slower. But basically, the solution is walking along that eigenvector in that direction if you looked at it as a function of time in the phase portrait. How about the other one? So we'll let C1 be 0 and C2 equal 1, so all we have is a second. So all we're looking at is y of t equals e to the lambda 2t times v2. So if we start here, say this is our initial condition, lambda 2 is positive, we're going to be walking in this direction. So if we start on the second eigenvector v2, we're going to stay on it. And because we have positive eigenvalues, we'll be moving away from the equilibrium solution at the origin. Let me erase this for a second. So that is why you can barely see that along these eigenvectors you see arrows. I will make them a little more prominent. And they're pointing away from the equilibrium solution at 0 because this is a source and all these solutions are moving away from it. Okay. Now what happens when you're not directly starting on an eigenvector? You're starting someplace out here. Well, then you have a combination of contributions from both eigenvectors, both solutions. I'll show you what that looks like in a second. So here we go. Let's say you start right here. You're not starting on V1, you're not starting on V2, you're starting somewhere in between. That's because C1 and you have contributions C1 and C2 from both eigenvectors. You're still going to be moving away. Okay, from the origin. But the solutions end up looking kind of U-shaped, but they aren't going to go through the origin, right? You start here, you're going to be moving away. You start over here, you're moving away over this way, and down this way. You can kind of see it from the direction field that's behind it. Now, you really can't tell a lot until you actually plot some of these, or the particular one you're interested in, but something you can figure out right away is here is this eigenvector has a value of 2. This has an value of only 1. As time goes on, which one is going to be the more significant ones? It's going to be the bigger one. Remember, your solutions look like this. In this case, it would be C1 e to the t times v1 plus C2 e to the 2t times v2. Okay, as time goes on, this gets to be more prominent than this one, and so it has more influence over the solution. In fact, as time approaches infinity, this one becomes almost not much of a contribution at all. And you can see that in here. So as time goes on, this solution is going to start looking more like it's going in the direction of V2, because here is that larger eigenvalue. You see, they look like this. Okay, they're kind of starting to look like they're going to the direction of V2, and that's in either direction. Let me clear this off a minute to show something else. Let's say the situation was reversed. Okay, I'm going to have to draw over this diagram. Let's say this was 1 and this was 2. Okay, the solutions would start out here, and they would start looking like they're going in this direction. They'd start looking like V1s. Right, I just wanted to show you the contrast so you kind of get an idea. They'd still be sources. The way to really pick out the source is just look at the arrows along the eigenvectors. They're moving away. Remember, a source in the first order equations in chapter 1, the unstable ones were both moving away on the phase line. Well, it's similar here. This is a source. They're moving away. You can think of them as you don't call them unstable, you just consider them a source. Now, all the steps for the sink are identical to the source, because the only difference, which wasn't taken into account at all when we found the eigenvectors, is that for a sink, no, I will not learn this. Okay, I always think it has the pin, and it really has this square business. Okay, both of the eigenvalues are less than 0. Before, they were both positive, greater than 0, and they gave you a source. Now they're both less than 0. It gives you the sink. Solutions look the same. It's just that as you plot them, these are going to be negative. And here's the canonical sink. So we have two eigenvectors. I'm sorry, two eigenvectors and two eigenvalues. The first one is -1. The second eigenvalue is -2. You can pick out immediately this is a sink by these arrows right here on the eigenvectors. So they're both pointing towards that equilibrium solution, which is at the origin. So if you start here on this eigenvector, you're going to be moving toward the origin. Of course, you never get there, but you're moving toward the origin, and you're moving at a rate of e to the minus t, because this first eigenvector is -1. In this case, you're moving even slower, because it's going as e to the minus 2t, because this eigenvalue is -2. If you are off the eigenvectors, you have a combination of those two contributions from both, you're still moving towards the origin, because this is a sink. So everything's coming in towards it. Okay? And you'll notice it sort of follows in here, coming along eigenvector v1, and the reason for that is that this eigenvalue is the least negative. So if I write the solutions, I've got y of t is c1 e to the minus t times v1 plus c2 e to the minus 2t times v2. As t increases, this starts looking more and more like 0, and this term dominates. And that's why it's coming in along the V1. It's like it's sort of asymptotically coming in along that first eigenvector, and that's because the first eigenvalue in this case is less negative than the other one. Now we'll look at the saddle. This is going to be the canonical saddle, and for the saddle, one eigenvalue is negative, one eigenvalue is positive, but for this example we'll say their absolute value is the same. That makes a nice symmetric pattern. Solutions are the same, the eigenvectors are the same. So here is the saddle pattern. All right. This eigenvalue is positive. If you start here, you're going to be moving out because it's a positive eigenvalue. This one's negative. If you start on the second eigenvector, you're going to be moving down towards that equilibrium solution at the origin because this eigenvalue is negative. So if you're starting over here, where do you go? Actually, you start lining up with the positive one because here's the solution. Y of t is c1 e to the t times v2 plus c2 e to the minus t, v1 and v2. Well, as time goes on, e to the minus t is decaying to 0. So this is out of the picture, and the solution will look more and more like e to the t times v1. So that's why the solutions starting here start kind of going out along the first eigenvector v1 because it has the positive eigenvalue. So this is just a quick summary for the canonical example of a source, sink, or saddle. The simplest matrix is the coefficient matrix with the diagonal matrix with the two eigenvalues sitting on the diagonal. So it is lambda 1, 0, 0, lambda 2, and the two eigenvalues for this case are not equal to each other, and they're non-zero. So we have two distinct eigenvalues. For the source, both of these are positive. For the sink, they're both negative. For the saddle, they have different signs. The eigenvectors are the same in each case. V1 is along the x-axis, V2 is along the y-axis if you were using x and y. Okay, and here's the solutions. Now I'll do a non-canonical example. This is one that was in the textbook on page 275. So again, we have our system written in matrix form. That's what's here. And we have this particular coefficient matrix, 2, 2, 1, 3. The trace of A is 5. The determinant of A is 4. 6 minus 2 is 4. Okay, so the determinant is not 0, so we know that the only equilibrium solution is a trivial solution at the origin at 0, 0. Also, if we look at what would be the determinant in the quadratic formula, t squared minus 4d, t squared is greater than 4d, so that's positive, so there will be two distinct real eigenvalues. And we can have a source, a sink, or a saddle depending on their sign. So now we'll find the eigenvalues. So first we'll look for the characteristic equation. So here's the So here is the characteristic equation equaling to 0, and I substitute those values in for the trace and the determinant. Remember that there's always a negative sign in front of the trace. See that negative sign right here? Okay. And now we have to find these. We could find them using the quadratic formula as stated before, or in this case we can just factor it. It factors to this, giving us two eigenvalues, 4 and 1. They're both positive, so we have a source. So now we know these two eigenvalues, we have to find the eigenvector. So to find the eigenvector, we substitute each eigenvalue into this equation and solve for the components of the vector v. So this is the first case. Remember that the first eigenvector is 4. So here's your A matrix, 2, 2, 1, 3, and you subtract 4 along the diagonal and end up with minus 2 and 2, 1 and minus 1. And you'll notice something about this. It's sort of these are multiples of each other, right? If you took minus 2 times the second line here, you get minus 1. That's to be expected because A minus lambda 1I is 0. The determinant of it is 0 when lambda equals lambda 1 or lambda 2. So that's to be expected. So we'll try to figure out what to do about Vx1 and Vy2. I usually write it out. So I've got minus 2 Vx1 plus 2 Vy1. That has to equal 0. You can write the second line out, but it's no more information than you have right here. Okay, so basically it's the same thing. You would have, well, factor out a negative 2 and get Vx1 minus Vy2, Vy1 equals 0. The only way for this to hold is if they're equal, right? So you need Vy1 to be the same as Vx1 for this to be equal to 0. So when you add them, for them to be 0. Okay, so they have to be equal, so you always pick the simplest thing. I'll pick 1, 1. Let Vx1 be 1, then Vy1 is also 1. And that's my first eigenvector. Now repeat the process for the second eigenvector. So here's for the second eigenvector. I've substituted the second eigenvalue into this equation, looking for the components of V2. And the second eigenvalue was 1. So you see the 1 being subtracted off of the diagonal elements of A, and this is what you get. Okay, let's write it out. So I have Vx2 plus 2 times Vy2 has to equal 0. Alright, you can pick one of them, and obviously if you pick Vx2 to be 1, then Vy2 has to be minus 1/2. Well, minus 1/2 is kind of hard to write, so I'll do it the other way. I'll let Vy2 be 1, and if it's 1, then Vx2 has to be minus 2. So here is the second eigenvector. So the first one was 1, 1, and the second one is minus 2 and 1. Are they linearly independent? Yes, they are. They are not multiples of each other. You could put them in a matrix and take the determinant, and you would get non-zero value. So while they are linearly independent, they are not as simple as a canonical case. They are not lined up with the coordinate axis. They're still straight lines, but they're not lined up with the coordinate axis. So here's your V2 minus 2 and 1. Here's V1, and that is a diagonal line. We can draw these outgoing arrows on these already because we know that it's a source. Both eigenvalues are positive. So here's the solutions. Okay. Here was the first eigenvalue, has a value of 4. Here's our eigenvector, 1, 1. Here's a second eigenvalue, which was 1. Okay, and the second eigenvector, which is minus 2 and 1. So when we write out these solutions, they are not decoupled like the canonical example was. X of t is going to be, there's a 1 here, so that's c1 e to the 4t, and now it's multiplied by the minus 2, so it's minus 2 c2 e to the t. And y of t is c1 e to the 4t again, and then it's just plus c2 e to the t because it's only being multiplied by a 1 and not by a negative 2. Note which one has a larger eigenvalue. Okay, it's this, it's the V1. It was the one that was going like this. This was V1. Okay, so the solutions are going to start to approximate the slope of V1 as time goes on. So here's the result. We have the two eigenvectors sitting here. Here's V1, here's V2. Arrows are going out from the equilibrium solution at the origin because the two eigenvalues are positive. This eigenvalue is largest, so as time goes on, the solution, it starts here, it's going to be going towards infinity, but it will be going more or less in the direction of V1 because it has the larger eigenvalue. So that's it for source, sink, and saddle. These are the cases where you have two distinct non-zero eigenvalues.